Good morning everyone. Welcome to the second lecture of our week number 3 where we are talking about the one dimensional steady state heat conduction scenario. Now in the previous lecture we have seen the situation with a plane wall. Basically we started with the generalized heat diffusion equation in the Cartesian coordinate, then we simplified that by removing the transient term, then removing the heat generation term, and then also reduce the space dependence just to one coordinate. Accordingly, the corresponding partial differential equation got reduces to an ordinary differential equation, and then we have seen how we can solve that to analyze simple conduction scenario. And we have also seen the concept of thermal resistance, or how can we use the concept of thermal resistance in such conduction analysis, so that we do not need to solve the ordinary differential equation always, rather we can just calculate the corresponding thermal resistance and get the rate of heat transfer, and that concept is even more useful when we are dealing with a composite wall just like this. Very similar to the electrical systems, we can consider the given system to be comprising of several such kind of thermal resistances, and accordingly we can form an equivalent thermal resistance circuit and do the analysis. This is called the electrical analogy of heat transfer. Like the situation shown here, from there like yesterday, as long as we are sticking to the Cartesian coordinate system, then we can write that as we have learned yesterday, Cartesian coordinate, the representation being in the form of a plane wall. There we have seen that the thermal resistance, let us say corresponding to conduction, can be given by L upon K into A, where A is the length scale associated with the direction on which the heat is being transferred, A is the cross section area, the area perpendicular to which this heat is being transferred, and K is the corresponding thermal conductivity. And we have seen similarly the thermal resistance corresponding to convection can be given as 1 upon H into A, H being the convective heat transfer coefficient, A again is the area perpendicular to the direction of this heat transfer. And when we are having multiple such kind of layers comprising of conduction and convection, or sometimes in some cases can be radiation, then we can easily calculate the thermal resistances for each of them to form an resistance circuit. So, just for completeness purpose, let me add the thermal resistance that we can get corresponding to radiation. I am not deriving it here because that we have done in the previous week, where we introduced the concept of thermal resistance for both convection and radiation situation, and also drawing analogy with the convective thermal resistance. We can also write this one to be equal to 1 by H r into A, where H I refers to the radiative heat transfer coefficient, which we know that can be represented as a product of emissivity of the corresponding surface into the Stefani-Boltzmann constant into T1 square plus T2 square, T1 and T2 being the temperatures across which this heat transfer is taking place, by T1 plus T2, and then this is the corresponding expression for the resistances. And this particular diagram that is shown here, yesterday we have done analysis here. This situation where we can see convection is happening on either side of the wall, and the wall itself is comprising of 3 different layers. We can visualize 5 different resistances. This is the one corresponding to the convective heat transfer associated with the hot fluid side, this is the convective thermal resistance associated with the cold fluid side, and in between we have the 3 conduction thermal resistance, 1, 2 and 3 corresponding to each of the layers. And as the area associated with each of the 5 modes of heat transfer are same, so we can assume that all of them are connected in series, and also the same amount of power that is passing through all of them. Therefore, we can easily connect them through a series, just analogous to what we do in electrical circuit, and then calculate the equivalent resistance. The equivalent resistance for such a circuit can be just summation of all the individual thermal resistances. And also we have introduced the concept of overall heat transfer coefficient, where the product of overall heat transfer coefficient into the corresponding area is defined as this equivalent resistance. So, we can also calculate the overall heat transfer coefficient at any specified area once we know the value of the equilibrium the equivalent resistance for the circuit. And when the areas are different, then we have to visualize them to be connected in parallel, and accordingly we can perform the analysis as well. Now, the way we have presented here, here we are assuming that just look at this particular surface which is connecting this material or layer A and layer B. Here while writing this expression in this particular format, we are assuming that the contact surface connecting layer A and layer B is a perfect one. There is no irregularity between the irregularity on the surface, and on each point of the surface both A and B are tightly connected with each other. But that may not be true in practice, because in several scenarios practical surfaces can be rough, they may have certain irregularities, and accordingly, like suppose your surface A may be of shape like this, whereas surface B may have a shape somewhat like this. Now, if you connect them, then what will happen? If this is the way you are connecting them, ideally they should have been connected just along this line, but practically the contact surface may have lots of variations or pores, something like this. Now, this intermediate portion which I am showing by this hatched line, these portions are voids, they are generally filled by air, or if there is some liquid or other gases that can ingress into this, they are filled with that. And accordingly, the concept of contact resistance comes into picture. Contact resistance refers to exactly what I am talking about. The layer A and B are connected with each other, and once we zoom this connection using a microscope or some similar device, you will find lots of discontinuities, lots of pores. And these voids, once they are filled up with certain material like air, then they also will lead to some kind of resistance, or they are also going to offer certain additional resistance to the heat transfer, because the thermal conductivity of air generally is expected to be much lower than corresponding solid materials, and therefore, the heat when it is passing through these voids, passing through these pores, they will face additional resistances, and that resistance is referred as this contact resistance. Like if suppose for unit area of the interface, say for unit area of interface, suppose we are talking about at one point where the temperature is T, another point the temperature is Tb, then the corresponding thermal resistance at this contact surface, and we are putting the double prime symbol to indicate that we are going to use heat flux, is given as Ta minus Tb upon the corresponding heat flux, the conduction heat flux, that is where we are talking about the heat transfer that is taking place in this direction. Or to put in a better term, just for better convenience, let us talk about this point. Here let us put the temperature is T1, and at this point the temperature is T2. Then as per this diagram, if we talk about this heat transfer, then corresponding thermal resistance will be equal to T1 minus T2 divided by Q double prime of this gap. So, this additional resistance now also needs to be taken into consideration while forming the circuits for thermal resistances. Of course, the nature of or the magnitude of this thermal resistance depends upon the surface, the nature of the contact depends upon both layer A and B, and also by modifying the nature of this gap, we can modulate the value of this resistance. Like suppose if these gaps are vacuum, then what will happen? Then there is nothing which can be used to transfer the heat, and you know that both conduction and convection require certain kind of medium for transport of heat. So, if the pores are vacuum, then there will be no heat transfer through them at all, and accordingly the heat will only get transmitted through this connected portion, through these portions there will be no heat transfer. So, the total contact resistance will be much more significant in that case. On the contrary, if we can somehow fill up these gaps with some conducting liquid, then there will be an increase in the thermal conduction property through this gap. So, the contact resistance will decrease. These are the certain values for contact resistances for certain common situation. Like if you are talking about the vacuum interface, for stainless steel, the value of this thermal resistance will be in the range of 6 to 25 into 10 to the power minus 4. This notation, it indicates that whatever values they are given, their R double prime after multiplying R double prime with 10 to the power 4. So, here with stainless steel we are actually talking about values of contact resistance to be of the order of 6 into 10 to the minus 4. Similarly, with aluminum it is slightly lower because aluminum has a higher thermal conductivity compared to stainless steel. If the interfacial fluid is air, then we are having 2.75, whereas if you are using something like glycerol, resistance is lesser. These are certain interfaces of metal combinations or material combinations. You can see when we are having aluminum coupled with aluminum with indium foil filter, then it is only of the order of 0.07, or you can say it is 0.07 into 10 to the power minus 4, in that range. Similarly, when silicon chip has been coupled with aluminum with 0.02 millimeter epoxy, it is in the range of 0.2 to 0.9 into 10 to the power minus 4. And also note the unit for this one. Here we are also having the meter square in the numerator, because we are expressing this one in terms of heat flux and not in terms of power. So, contact resistance is another important parameter while dealing with the real surfaces, and to mathematically calculate the rate of heat transfer through such contact resistance, we need to know precise value of this contact resistance, otherwise we can't do it, and for that we generally have to depend on certain kind of experiments and maybe certain analogies with real life situations. Let us now solve one numerical problem to use this concept of use the concept of thermal resistance. I am not putting the contact resistance in here, I am just talking about thermal resistances. Now, here my situation is, I am talking about a human which is having a body core temperature of 35 degrees Celsius. He is exposed to an environment maintained at 10 degrees Celsius. He is wearing a suit made of special kind of insulation, the corresponding thermal conductivity of insulation for that suit is mentioned. Emissivity of the outer surface of the suit is 0.95. So, radiation heat transfer is also relevant, and we have to determine the thickness of the insulation required and corresponding skin temperature if the rate of heat loss is restricted to 100 watts. We have to consider the human body to include a flat layer of 3 millimeter, corresponding thermal conductivity of flat layer is also given. This is somewhat kind of schematic representation. This is the core surface, this surface is the core body, then we have the fat layer of 3 millimeter thickness, and then we have the insulation. So, this is our body core and this is the skin, in between you have the layer of fat. So, this Ts here refers to the skin temperature which we have to find at the end, and the insulation corresponds to the suit that he is wearing. So, this is the thickness of the insulation, thickness of the suit, which also you have to identify. Emissivity and of the outer surface and thermal conductivity of the insulation material is given, and to the outer surface we can say that the temperature is 10 degrees Celsius, and it is not given, but we can consider two kinds of scenarios. We can have air flowing over this surface at 10 degrees Celsius, this is the corresponding heat transfer coefficient, whereas when water is flowing the heat transfer coefficient will be much larger, let us say it is 100 times more than air. We shall be solving for both the scenarios, but quite a few assumptions that we have to put. The standard assumptions, one is steady state we have to consider, then 1D heat transfer. Let us say this direction is the x direction, then the entire heat transfer is taking place only in this direction. Then we are talking about constant value of the thermal conductivities for both the materials. Similarly, the emissivity is also constant, and so is the heat transfer coefficient for air or water, whatever mean the working medium. And another consideration that is related to the radiation application, here this we are assuming the body or this outer surface of the insulation layer, its total area to be too small compared to the area of the room, so that we can assume it is having radiative heat transfer only with the wall maintained at 10 degrees Celsius. So, we have to form the circuit of thermal resistances. Find the modes of heat transfer. How many modes of heat transfer involved here? All the 3 modes. Firstly, from here up to this it is conduction, from the core to the skin by conduction, then again conduction from the skin through the insulation to the outer surface. Remember, here we are not talking about any kind of contact resistance at this point, it has been assumed that the contact resistance is 0 in this situation. Then from the outer surface of the insulation, heat can go to the surrounding following 2 modes. As some kind of fluid, air or water is flowing over the surface at a lower temperature, so there will be heat loss by convection. Similarly, there will be also radiative heat loss. So, this is the corresponding corresponding resistance circuit that you can think of. This is the conduction resistance corresponding to the fat layer, this is the conduction resistance corresponding to the insulation, this is the convective resistance and this is the radiative resistance from the surface to the outer surrounding or outer air. Now, we have to calculate each of the resistances separately. So, how we can form or calculate the equivalent resistance in this case? Our equivalent in this case can be the conduction resistance corresponding to the fat layer, that is LSF as per the notation shown on the figure, by K corresponding to the skin fat into the area, plus the conduction resistance to the insulation. So, L for insulation by K insulation into area, plus there are now two resistances, 1 upon HR into A and 1 upon H into A. Both of them are connected in parallel to each other, because at this point the temperature is the outer surface temperature and on this side the temperature is the surface temperature. So, the temperature across them are the same, but the amount of power transmitting through both of them, they are different, that is why you can assume them to be connected in parallel. And if they are connected in parallel, just the way you calculate the equivalent resistance for two electrical resistors connected in parallel, we can write this to be equal to 1 by H into A plus 1 by HR into A whole to the power minus 1. Now, other values are all given, but we have to calculate the HR. How can we get the HR? Here this HR actually talking about the radiation heat transfer that is taking place from the surface, from the exterior surface of the insulation to the surrounding. So, you can write its expression to be as epsilon into sigma into T. Let us say at this point the temperature is T E, to denote this is the exterior temperature. So, it is T E to the power 4 minus T infinity to the power 4, T infinity being the surrounding temperature, or epsilon into sigma into T square plus T infinity square into T E plus T infinity into T E minus T infinity. And one thing I missed here actually, the area, because I am talking about power and not heat flux. So, epsilon into sigma into A into T square plus T infinity square into T E plus T infinity, this entire thing we are clubbing together to get the heat transfer coefficient corresponding to radiation, and we are keeping T minus T infinity outside. Actually, I should not couple A here, A comes out, then the entire bracketed terms becomes our HR into area into T minus T infinity. So, from this the information given informations, we have epsilon here as 0.95, sigma the Stephen Boltzmann constant. Do you remember its value? The value of sigma I told earlier also, it is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So, this value of sigma that you can put here. Area is not given, but we can for the moment assume area to be 1, because area is appearing in each of the resistances, and then we have T E and T infinity. T infinity is 10 degrees Celsius, but while doing this we have to remember that the temperatures need to be expressed in Kelvin, as we are talking about radiation. So, let us convert T I to Kelvin. So, it is 35 degrees Celsius means it becomes 308 Kelvin. This is 10 degrees Celsius. So, your T surrounding becomes 283 Kelvin. So, we know T infinity of T surrounding, but this T E, the T exterior which is acting at this particular point, this is not known yet, and unless if that is not known, it is not possible to calculate the value of this H R. So, we are assuming some value of H R in this case. Let me provide you the value of H R to be equal to 5.9 watt per meter square Kelvin. This value can be obtained through an iterative calculation. I am directly giving you the value. Once you have the value of H R, then you can easily calculate the value of R equivalent. So, what will be your R equivalent? The expression that I have written, from there L for the skin fat layer, I am writing the same thing again, into area plus L for the insulation layer by K insulation into area plus 1 by H into A plus 1 by H R into A whole inverse. So, the last term maybe we can couple them together. So, 1 upon H A plus 1 upon H R into A, if we take 1 upon A common from this, then it becomes H into H R by H plus H R, and now as we are taking the inverse of that. So, it becomes L S F by K S F into area plus L I N S K I N S into area. So, it is H plus H R by A into H into H R whole inverse. Now, this is the R equivalent that we are getting, and it is mentioned in the problem that we want the rate of heat loss to be restricted to 100 watt. So, using this R equivalent, we can write that R equivalent should be equal to your interior temperature T I minus the surrounding temperature T infinity by Q dot. That should be your R equivalent for this. Now, in this case it is mentioned that T I and T infinity, the values we had. So, it is 308 minus 283 by 100, that is equal to 0.25 Kelvin per watt. Actually, I have made a mistake while writing this. This is not the proper way of writing, because what should be your convective resistances? We can straightway write as they are connected in parallel. So, it should be 1 upon H A plus into 1 by H R into A by 1 upon H A plus 1 upon H R into A. I missed one reciprocal symbol. So, it is 1 upon H A into 1 upon H R into A by 1 upon H A plus 1 upon H R into A. So, if we put it here, one area cancels out from the denominator, and so it becomes just 1 upon H R into A square, and here it is 1 upon A into H plus H R by H into H R. So, if we eliminate the area and also this H R product, then correspondingly it just becomes 1 upon A into H plus H R. So, once we have got the values, then using that R equivalent, what we can write? R equivalent is equal to, taking this 1 upon A constant, or sorry, common from this, R S F by K S F plus L I N S by K I N S plus 1 by H plus H R. So, from there we have to separate out the information, as our objective is to get L I N S. So, we can write L I N S is equal to K I N S into A into R equivalent minus L S F upon K S F minus 1 by H plus H R. Now, what about the area? How much is the area that is given? The area information is again not explicitly given in the problem. Now, typical in the true sense in the problem the value was given, I have omitted that because I want to discuss about that. Like the way I have shown how to calculate the H R, which made needed iterative calculation, was finally assumed in value. For the A also we have to take a value, and generally the outer surface of the human body can have an area of approximately 1.8 meter square. So, if we put that here, then K insulation was an extremely small number 0.014. So, 0.014 into 1.8 into R equivalent we have got to be 0.25 minus L, the thickness was 3 millimeter with a thermal conductivity of 0.3 watt per meter Kelvin. So, 3 millimeter is 3 into 10 to the power minus 3 by 0.3 minus the heat transfer coefficients for. Now, here there is a difference whether to do with air or whether to do with water. Let us consider air, which is 2 and HR is 5.9. So, 2 plus 5.9. So, putting this, I have pre-calculated the number, it will be coming something like 4.4 millimeter. So, this is the insulation thickness that we need for that suit. And the second parameter that we have to calculate is the skin temperature, that is the temperature T s at this particular point that we have to calculate. Now, how can we calculate that one? We know the rate of heat transfer now, the same Q dot is going to flow through all the layers, then how can you use that? So, if we consider only that inner layer, then corresponding to that layer we can write T interior minus T s divided by Q dot should be equal to the resistance corresponding to the skin fat layer, which is L S f by K S f into area. From there we can write that T s is equal to T I minus L S f into Q dot upon K S f into area, and T I as per our in given information it was 308. So, it is 308 Kelvin minus L S f, we have seen that to be equal to 3 into 10 to the power minus 3 into the area of the body was 1.8 meter square. K S f was a very small number, that is 0.3, sorry, the area comes in the denominator. So, it is into 1.8 and it was the Q dot was 100 watt. So, if we put all the numbers, then the T s will be coming to be something like 34.4 degrees Celsius. So, you can see the temperature here was 35 degrees Celsius and the on the skin it is 34.4 degrees Celsius. So, there is very little difference. However, following the same way you can calculate this T e also and you will find obviously difference there. If we want to consider or repeat the same calculation considering water as a surrounding fluid, then you have to replace this 2 here by 200. And if you do the calculation, you will find that in that case the required thickness of insulation will be approximately 6.1 millimeter. Please do this calculation, and also I would request you to calculate the value of this T e, the exterior temperature. How can you do that? If we consider the insulation layer only or heat transfer through the insulation layer, then T skin minus T exterior divided by Q dot is equal to L I n s upon K I n s into area. So, from there you can get this T exterior, just check what values you are getting corresponding to both the materials. Do you what should be the value of this T s with what is the working medium? Only this one only, the same. Why? Look at the expression. In that expression the convective heat transfer coefficient is not coming, and as the Q dot is same regardless of the exterior fluid. So, the expression remains the same and the calculation procedure is same, and you will be getting the same value of T s and also the same value of T e for both the cases, or sorry, same value of T s, but the value of T e may be different. Just calculate and check that out. Now, I am going to something known as an alternate approach. The thermal conduction based or thermal resistance based approach is very useful. As we have seen, we can easily identify each of the thermal resistances, connect them in series and parallel, and we can have an equivalent thermal resistance circuit to solve for. However, there is one important assumption that we have taken while doing this, that is we have assumed the thermal conductivity to be a constant. But if your thermal conductivity is not constant in the x direction, then if the thermal conductivity is not constant in the x direction, or if your system is suffering from a change in the cross section area in the flow in the direction of heat transfer, then that thermal resistance concept becomes invalid, and then we have to go for this alternate approach. Here I am going to take you back to the development process of that heat diffusion equation. The generalized heat diffusion equation that is developed in the Cartesian coordinate, in one of the earlier steps of that we got an expression of this form, dou q dot x dou x minus dou q dot y dou y dou q dot z dou z plus q 0 triple prime was equal to rho c dou t dou t. Now, if we put our conditions which we are always doing, that is if we restrict ourselves to one dimensional heat conduction under steady state and no heat generation, then what we are going to get, this equation becomes simpler, the y and z direction can be neglected and the transient part also heat generation goes off, leaving us dq dot x dx is equal to 0, which gives q dot x is not a function of x itself. That means, q dot x or heat transmission rate in the x direction actually remains to be a constant. So, as long as we are talking about this Cartesian coordinate in plane wall, the conduction heat transfer rate is a constant under steady state one dimensional scenario without any heat generation. See, here we are not talking about any variable thermal conductivity or constant thermal conductivity, it is equally applicable for both of them, because we are yet to introduce the Fourier's law of heat conduction. Then what is your Fourier's law of heat conduction? We know that as per Fourier's law, q dot x will be equal to minus k a dt dx. Of course, we are using one dimensional condition, so we are straight away writing dt dx. Now, if we rearrange the terms a bit, then what we can do, depending upon whether your parameters are variable with space coordinate or constant with the space, then maybe we can write this one to be something like q dot x into dx upon area equal to minus k dt, because commonly k is a function of temperature, k depends on temperature. So, we are clubbing k with this, and now we are putting the integration sign this dx this equal to minus of k dt, and the integration is to be performed from some x1 to x2 where the temperature limits being T1 to T2. And once we know how area is varying with x and how k is varying with temperature, you can easily do the calculation. If a and k, a is constant and k is also independent of temperature, then this one reduces to the earlier concept only, that is the special case where a and k both are constant. In that case, what you are going to get? In that case, you are going to have q dot x upon area into delta x is equal to minus k into delta t, and if you rearrange this one, then delta t upon q dot becomes delta x upon k into a, and the negative sign is there, which indicates that the heat transmission is taking place in the direction of reducing temperature, and this expression is nothing but the thermal resistance that we have used. So, the concept of thermal resistance can be employed only when we are talking about constant thermal conductivity and no area change in the direction of heat transmission, but when either of them or both are present, then it is better to go for this alternate approach, where we are making use of the information that the heat transfer rate is independent of x direction, it remains constant as long as we are talking about steady state one dimensional heat conduction without any heat generation. To demonstrate this, I have this problem for you. Here you are talking about a conical section which is having circular cross section with diameter d equal to ax. So, in the flow direction here, or rather heat transfer direction, this is your x direction, x1 is this point where the value is given to be 50 millimeter or 0.05 meter, on the other end it is 0.25 meter. temperature is given to be 400 and 600 kelvins respectively. So, we have to calculate the rate of heat transfer through this cone. Here the thermal conductivity of the material is also given to be 3.46 watt per meter Kelvin. Here the thermal conductivity is constant, that is independent of temperature, but the area is changing because the diameter is changing in the direction of heat transmission. Here the direction of heat transmission is actually in this, because from 600 to 400 it will get transmitted, but we are not talking about this, we are just sticking to the conventional x direction, which is from this smaller end to the larger end. So, going back to the general expression, q dot x is equal to minus k a dt dx, or q dot x becomes q dot x into dx upon a is equal to minus k dt. Now, in this case we know that the diameter is equal at any particular location, diameter d is equal to a into x, or the value of a is also given. Then the cross section area at a particular location a will be equal to pi by 4 d square, that is pi by 4 into a x whole square. If we put it back here now, q dot x dx pi by 4 a square x square is equal to minus k dt. A and k being constant, then and also q dot x is also a constant. So, we are writing this as 4 by pi into q dot x upon a square into dx upon x square is equal to minus k d dt. Integration performed from x equal to x1 to x2, corresponding temperature limits are T1 to T2. So, continuing with this, we have 4 by pi q dot x upon a square into, it is x to the power minus 2 we have. So, once we are integrating this, integration of dx upon x square, we are going to have integration of x to the power minus 2 dx. So, putting the performing the integration without using any constant of integration. So, we shall be having x to the power minus 1 upon minus 1, that is minus 1 upon x. So, accordingly the minus sign we are taking outside. So, it is 1 upon x 2 minus 1 upon x 1 is equal to minus k into T 2 minus T 1, or q dot x is equal to then. So, it is pi a square into k to T 2 minus T 1 divided by 4 into 1 upon x 2 minus 1 upon x 1. So, you can put the limits here now. This is the expression for q dot x. We have got a closed form expression of q dot x. In this case, all the values are given. If you put the numbers for this particular problem, then q dot x will come as pi into a is given as 0.25. So, 0.25 whole square into k is given as 3.46 divided by 4 into 1 upon x 2 is 0.25 minus x 1 is 0.05 into T 2 minus T 1, T 2 is 600 minus T 1 is 400, and after solving this, q dot x is going to come as minus 2.12 watt. So, this is the final solution that we are looking for. Why it is the minus sign? It indicates that the heat transmission takes place in the negative x direction, and that is logical also, because your T 2 is higher than T 1. So, you can always expect the heat to get transmitted in this direction. The same is proved by this problem also. We have, as long as you are consistent with your symbols, your notations, then your solution should also indicate the direction of heat transfer, like it is doing here. And if your interest is to calculate or get a closed form expression for the temperature, let us say you want to get the expression for temperature at any intermediate plane, then how can you do that? There also we can make use of the expressions. In that case you can perform the integration something this way, 4 upon pi q dot x upon s square into integration of dx upon x square is equal to minus k dt. Perform the integration from x equal to x 1 to certain x, and then corresponding temperatures will be T 1 to T at that x location. In that case, on one side you will be getting minus k of T at x minus T 1, and the other side you have 4 upon pi q dot x upon s square into 1 upon x minus 1 upon x 1, and now you can rearrange the terms to get a closed form expression for T at x. So, this way you can solve using the alternate approach also when we are dealing with variable cross section area or temperature dependent thermal conductivity. So far we have restricted our discussion only to plane walls, that is only to the Cartesian coordinate, but in several scenarios we have to go to the cylindrical or spherical coordinate system as well. So, let us check out the 1D steady state heat conduction scenario in a plane wall. Like I have shown in the very first slide of yesterday's lecture, that under one dimensional scenario the generalized heat diffusion equation in cylindrical coordinate gets reduced to a form like this: 1 by r dt r of r k dt dr to be equal to 0. This is of course the same assumptions, I should repeat again. We are doing this for steady state, one dimension, and at the absence of any kind of heat generation. So, the r cancels out. So, we have d of r k dt dr to be equal to 0, which indicates r k dt dr to be equal to some constant C 1. Also, we know that the rate of heat transmission in the cylindrical coordinate direction q dot r will be equal to minus k into area in that r direction dt dr. Now, what is your area for a cylinder? Let us take one cylindrical object, something like this. This is the center line, and we calculate r in this direction. So, if the radius at this point is capital R and the length of the cylinder is L, then this total AR can be represented as the peripheral area as 2 pi r into L, or at any r location it will be equal to 2 pi r into L. At any r location the peripheral area corresponding to the cylindrical section has to be equal to 2 pi r into L into dt dr. That is, if we rearrange the terms now, so let us take this 2 pi L minus of 2 pi L out, then we are left with r k dt dr. And now, if we compare this one with the earlier developed expression, so this becomes minus 2 pi L into C 1, L being the length of the cylinder that we are talking about. So, this q dot r is constant, it is not a function of r. So, in the plane wall case we have seen that the rate of heat transfer remains constant. Similarly, in case of plane cylinder also rate of heat transfer, as long as we are talking about 1D steady state heat conduction without any heat generation, rate of heat transfer is constant. But what about the heat flux? In case of plane wall we have seen that if there are no parallel resistor kind of case, then all the surfaces are sharing the same area, and accordingly the heat flux also remains constant. Only if we are talking about one layer being divided into two parallel layers, we have a division of the heat flux, and we have a division of the total power transmission. Accordingly, the value of heat flux may also change. Truly, but I am leaving this question open to you. Do you really feel the value of heat flux will also change in that case? Value of power definitely changes, but what about heat flux? Just think on that. But that is not true for plane cylinder cases. In case of plane cylinder, as we are moving from one layer to the another layer, the heat flux in the radial direction should be equal to the q dot r divided by the area of that layer, which is this 2 pi r into L, that is it is a function of r. So, the value of heat flux that keeps on changing at every location, but the power remains the same, that is because of the change in the peripheral area. Now, let us continue with this one. So, we get dt dr is equal to C 1 upon k into r. Now, if the value of temperature has to be finite at r equal to 0, that is for T to have some finite value, because if you put r equal to 0 here, you are getting dt dr to be infinity at r equal to 0, but that is not possible. So, therefore, dt dr in order to have t have some finite value, then this C 1 has to be equal to 0. So, we get dt dr to be equal to 0 in this case, and now you can continue from this. But generally we do not need to analyze cylinder from this way, rather we are more interested in hollow cylinders, just like the configuration shown here. Here we are talking about an hollow cylinder or an annular section where the inner radius is r 1, outer radius is r 2, and we are going to now analyze for this particular one. So, we have just seen that q dot r was equal to minus 2 pi L into that C 1, and our temperature expression was dt dr is equal to C 1 upon C 1 upon r. Here actually k also I am considering as a part of this. So, accordingly T, if we integrate this one, is going to be C 1 ln of r plus C 2. So, if we are talking about a solid cylinder, then C 1 becomes equal to 0, but if we are talking about a hollow cylinder like the one shown here, then of course, C 1 and C 2 both will be present there. So, to get the values, say at r equal to r 1, T r 1 is let us say is equal to T s 1, at r equal to r 2, T r 2 is equal to T s 2. So, putting the numbers, let us try the first one. T s 1 is equal to C 1 ln r 1 plus C 2, T s 2 is equal to C 1 ln r 2 plus C 2. Combining these two, we can write that C 1 is equal to T s 1 minus T s 2, or rather r 1 being greater than less than r 2. So, let us write this way, is T s 2 minus T s 1 by ln r 2 minus ln r 1, that is C 1. From there we shall be getting C 2 to be equal to, we can use any one of the expressions, let us stick to the first one. So, it becomes T s 1 minus T s 2 minus T s 1 by ln r 2 minus ln r 1 into ln r 1. So, the expressions for C 1 and C 2 both we have now. So, let us take it back to the expression for T r that we had. So, T r was equal to T s 2 minus T s 1 r 2 minus log of r 1, that is C 1 into ln r plus C 2, which is T s 1 minus again that same bracketed term T s 2 minus T s 1 by ln r 2 minus ln R1 to ln R1. So, we can combine them to get a single expression as Ts1 plus Ts2 minus Ts1 by ln R2 minus ln R1 into log of R upon R1. So, we get a solution for the temperature distribution within the cylinder. But now, can we make use of the thermal resistance concept here? Of course, we can. For that, let me erase these things. For that, I have to make use of the expression for that heat flux or rather power that I had originally. So, we have seen that the expression for q dot r at any location can be given as 2 pi L into that C1. So, putting that into use, we have minus of 2 pi L into C1, that is Ts2 minus Ts1 upon ln R2 minus ln R1, or if we rearrange them in a form as Ts2 minus Ts1 upon q dot r, then what we can write for this on the right hand side, we can write as ln of R2 by R1 by 2 pi L. Another way we can do it, just to get a better feel, just start from the basics, because these expressions actually in a not true representation, it is dependent on the C1 expression. Then q dot r at any location will be equal to minus k into A, that is 2 pi r L into dt dr. So, it is equal to k into 2 pi r L and dt dr, the expression of dt dr that you can get by differentiating this one with respect to r. So, this becomes Ts2 minus Ts1 by ln R2 upon R1 into 1 upon R, as 1 upon R and R cancels out. So, we are left with 2 pi k L Ts2 by Ts1 ln R2 by R1. Why I am repeating the same thing? I did it earlier, but I erased and I have done it again, because the expression for C1 that we have used, the k was included there, which gave a wrong expression actually. That is why it is always better to be starting from the basic principles, which is this form of the heat flux. Now, if we rearrange again in this form, Ts2 minus Ts1 by q dot r, then what you are getting? It is log of R2 upon R1 by 2 pi k L. That is the resistance, thermal resistance that you are getting associated with the conduction in a plane cylinder. So, the nature of the expression is definitely different. For plane walls, you got just L upon K A, very straightforward expression, where we are getting a logarithmic expression in this case, involving both the radius R1 and R2, the length of the cylinder L, and also the thermal conductivity of the corresponding material K. What will be the convective resistance on any one of the surface, say surface R1? At surface R1, the rate of convective heat transfer at R equal to R1, how much will be that? If H1 is the corresponding heat transfer coefficient, it will be H1 into corresponding area. How much is the area? 2 pi R1 into L into T at S1 or minus T at infinity. So, Q dot is equal to 1 upon 2 pi H R1 into L. This is the convective thermal resistance. Similarly, at the outer surface, Q dot convection at R equal to R2 is equal to H2 into 2 pi R2 L into outer fluid, let us say, okay, inner fluid was marked as T infinity 1, let us stick to that notation. So, here T infinity 2 minus T s 2, accordingly T infinity 2 minus T s 2 upon q dot becomes 1 by 2 pi H 2 R 2 L. So, we can see that the system that is shown in this case an hollow cylinder with a fluid passing through the inner surface or passing through the inner hole and another fluid flowing over the outer surface can be represented as a combination of 3 resistances. This is the corresponding conduction resistance ln R 2 by R 1 by 2 pi k L, and this is the convective heat transfer coefficient or convective thermal resistance rather on the inner side. This is the convective thermal resistance on the outer side. The same thing can easily be extended to the composite cylinder. So, when the cylinder is having multiple layers, look at that, there are 3 layers plus there are 2 convections on inner and outer surfaces. So, for the layer A, we can write that the resistance corresponding to layer A, it has an inner radius of R 1 and outer radius of R 2. So, it will be equal to log of R 2 upon R 1 by 2 pi into K A, if K A refers to the thermal conductivity for layer A, into L. For layer B, R B will be equal to log of the higher radius to the lower radius. Higher radius is in this case is R 3. So, it is R 3 upon R 2 by 2 pi K B into L. Similarly, for material C, R C will be equal to log of R 4 upon R 3 by 2 pi K C into L. These are the 3 conduction resistances. On the inner side, where the radius is R 1, we are having convective heat transfer characterized by the coefficient H 1. This is the corresponding convective heat transfer coefficient, convective thermal resistance. This is the convective thermal resistance on the outer side. So, we have a combination of 5 resistances. So, you can easily calculate R equivalent as a combination of these 5 resistances, and that can be expressed as the ultimate temperature difference T infinity 1 minus T infinity 4 divided by the net rate of heat transfer, and we can also calculate U A as 1 by R equivalent. Now, you can see here, while the R equivalent is same for all the surfaces, the value of U can keep on changing because the value of area also changes. Like if we want to define the value of this overall heat transfer coefficient corresponding to the inner surface, this one, then the value of corresponding area, like U corresponding to the inner surface into A corresponding to the inner surface, if we want to define this way, then corresponding area is 2 pi into R 1 into L. Whereas, if we want to define the overall heat transfer coefficient corresponding to the extreme outer surface U O, it has to be multiplied by the corresponding area, and this area is 2 pi R O into L, but both of them is equal to the R equivalent inverse or reciprocal of R equivalent. So, as R I and R, not R O, this is R 4 actually. So, as R 1 and R 4 are different, according to the value of U I and U O also will be different. U I will be larger than the value of U O. So, overall heat transfer coefficient may have different magnitude depending upon your choice of the area. It is not that much relevant for plane walls, but when you are into the cylindrical coordinate, then this is very much important. I shall be explaining a bit further on this curvilinear coordinate system. In the next lecture, we shall be solving numerical problems involving composite cylinders, and also we shall be dealing the situation of spheres, and we shall be calculating the thermal resistance corresponding to the spherical coordinate system. So, today we have discussed about the concept of contact resistance, and we have learned an alternate way of using the conduction heat transfer analysis when the thermal conductivity and cross section area are not constants, and then we have discussed about the heat conduction in plane and composite cylinders. So, that is it for the day. I shall be continuing tomorrow with the next part of this lecture. Thank you very much.